You think you know what temperature is, right? 30 degrees and sunny, a fever of 38, setting the oven to 200 Celsius. It's simple. But what if I told you that the scale we use every single day is, from a scientific standpoint, kind of broken? Today we're going from our familiar everyday Celsius to a scale that's way more fundamental, one that's built on the absolute laws of physics.
So here's what we're going to cover. We'll start with our familiar temperature scale and see why it's not perfect. Then we'll discover a scale built on a true absolute zero. We'll do some practical conversions and see how this absolute scale explains real-world physics like electrical resistance. We'll even look at the cool tools we use to measure it all and wrap up with the big idea. All right, let's get into it.
All right, let's start with what we all think we know. We have this built-in sense of what's hot and what's cold. But let's push past just the feeling on our skin and ask what's really going on.
So let's really think about that for a moment. When your weather app says it's 20 degrees Celsius outside, what is that number actually measuring? What physical thing is happening? It's definitely more than just a number.
And boom, here's the answer right from the source. Now don't worry about reading all that fine print, just focus on that highlighted part. Temperature is a measure of the average kinetic energy of molecules. That's it. That's the secret. Everything is made of tiny particles that are constantly jiggling and bouncing around. Temperature is just how we measure how fast, on average, they're all moving. Hotter means they're zipping around like crazy. Colder, and they're just kind of chilling out, moving slower. It's all about motion.
And this brings us to the two big players in our temperature story. On the left, you've got Celsius, our daily driver. It's useful, for sure, but it's totally built around one substance, water. And then on the right, you have Kelvin. It's not based on any one thing. It's based on the fundamental principles of energy itself. It's like the difference between a handy rule of thumb and a universal law of physics.
Okay, so what's the big deal? Why do scientists get so worked up about Celsius? Well, for starters, its 0 point is completely arbitrary. It's just the temperature water freezes at. Useful? Yeah, but not fundamental to the universe. And maybe more importantly, it has negative values. In a lot of physics equations, that's a total non-starter. You can't have negative energy or negative pressure, right? It just breaks the math. Plus, if you go up a mountain, water boils at a lower temperature. The whole scale shifts. So for the weather report, Celsius is great. For fundamental science, we need something better.
So if water's not a great anchor, where do you find a real zero? A 0 point that means something everywhere in the universe, not just here on Earth. Well, scientists found the answer in a pretty unexpected place, by looking at gases.
Yeah, this is where it gets really cool. Scientists were charting how the pressure of different gases changed as they cooled them down. And when they plotted this out, they saw something incredible. They noticed that no matter what gas they used, hydrogen, helium, you name it, all the trend lines pointed to the exact same spot. This, as one source calls it, magic mysterious temperature of minus 273.15 degrees Celsius. That's no coincidence. That's the universe telling us something.
And look at this graph from the textbook. It shows that exact moment of discovery. See all those different lines for the different gases? They're all sloping down, 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 and they all slam into the same point. That point, minus 273.15 Celsius, is what we now call absolute zero. It's the bottom, the coldest anything can possibly get. And that became the true non-arbitrary 0 point for a whole new scale, the Kelvin scale.
So, to put it plainly, absolute zero is the floor. It's 0 on the Kelvin scale, or minus 273.15 Celsius. It's the theoretical point where all that molecular jiggling slows to a near standstill. At this temperature, a substance has the absolute minimum energy it can possibly have. It's the ultimate cold.
All right, enough theory. Let's get our hands dirty and see how this works in practice. How do you jump between these two scales? It's actually way easier than you might think. Time for some simple math.
The real genius of the Kelvin scale is that a 1 degree change is the exact same size as a 1 degree change in Celsius. This makes the math super easy. To go from Celsius to Kelvin, you just add 273. And to go from Kelvin back to Celsius, you just subtract 273. That's it. Simple. We're using 273 as a nice round number here. Scientists use 273.15 for more precision.
And when you look at these textbook examples, you really see it. Take a look at the left side. Even something crazy cold like -200 Celsius is still a positive number in Kelvin. It's 73 K. See? No negatives. Because you physically can't go below 0 Kelvin. It's the absolute floor. And on the right, you can see 0 Kelvin is, you guessed it, -273 Celsius.
Okay, so who cares? Why does getting rid of negative numbers actually matter for real-world stuff? Well, this is where Kelvin goes from being a neat idea to an absolutely essential tool for understanding physics. Let's look at what happens inside a simple copper wire.
So let's check out this problem from the textbook. Remember our big idea. Temperature is just atoms wiggling and vibrating. Now, what's electrical resistance? Well, it's basically a traffic jam for electrons trying to flow through the wire. The more the atoms vibrate, the more they get in the way. So, what do you think happens to that traffic jam when you crank up the heat and make the atoms vibrate even more?
To see the real pattern here, we've got to ditch Celsius. It's just hiding the truth. So we do our simple conversion and add that third column for Kelvin. Now we're comparing the wire's resistance not to some arbitrary scale, but to the actual thermodynamic temperature. And this is the magic. When you plot resistance against the absolute temperature in Kelvin, you get a perfectly straight line. It's a clean, direct, linear relationship. More absolute heat means more atomic vibration, which means more resistance. It's a simple physical law that was totally hidden until we started using the right scale.
So let's follow that logic. If that line is perfectly straight, where is it headed? It points directly to zero resistance, at 0 Kelvin. And that just makes physical sense, right? If resistance is just electrons bumping into jiggling atoms, what happens when the atoms stop jiggling? The path becomes clear. As our source puts it, no vibrations mean no resistance.
Okay, we've got the theory down. But how do you actually measure this stuff, especially at the crazy high or low temperatures used in science and industry? Your little glass thermometer from the medicine cabinet just isn't going to cut it. You need some smarter tools.
Meet one of the workhorses of temperature measurement, the thermocouple. It looks complicated, but the idea is brilliant and simple. You just fuse two different metal wires together. You heat one end, that's the hot junction you see there, and a tiny bit of voltage magically appears between the wires. If you can measure that voltage, you know the temperature. They're tough, they're cheap, and they're used in everything from rocket engines to your kitchen oven.
So if you're an engineer building something, which do you pick? Well, it's all about trade-offs, as this table shows. A resistance thermometer, it's super accurate and predictable. That linear signal is a dream, but they can be a bit slow and bulky. A thermocouple, it's lightning fast, tiny, and can handle massive temperature swings. The catch? The signal's not linear, so you have to do some extra work to calibrate it. It's a classic engineering puzzle. Do you want pure precision or rugged versatility?
So you've got these instruments, but how do you know they're reading right? You need a rock-solid, unchangeable reference point. And that's where the triple point of water comes in. This isn't just freezing or boiling. This is a very specific, unique physical state where ice, liquid water, and water vapor all exist at the same time in perfect harmony. It happens at exactly 273.16 Kelvin. Because it's a fundamental constant of the universe, it's the perfect anchor point to make sure every thermometer in the world is speaking the same language.
And all of this brings us to the big takeaway. Switching from Celsius to Kelvin wasn't just about changing the numbers on the thermometer, it was a complete shift in thinking. It grounded our understanding of temperature in the fundamental laws of motion and energy, and that unlocked a whole new level of understanding of how our universe actually works.
But I have to leave you with one final thought, a little twist at the end. We said that at absolute zero, all that molecular motion is at its minimum. But does it truly, completely stop? Well, the bizarre rules of quantum mechanics have something to say about that, and they say you can never be perfectly still. There's always a tiny bit of residual energy, a zero-point vibration that can never be removed. It's a perfect reminder that even when you get to the absolute bottom, the universe is still buzzing with secrets.